Welcome back everyone. In this lesson we are going to learn about another interpolation technique, which is Lagrange interpolation polynomial. In the last lesson we have learned about Newton's interpolating polynomial, but right now we are going to see about the Lagrange interpolating polynomial. This polynomial technique is not just a new method, rather it's just an extension of the Newton's interpolating polynomial. So if you just go through all the slides that I have covered in this lesson, so you'll see that this is just an extension of the previous one. So let's move on. So first of all, as I have said, the Newton interpolation technique can be easily extended to the Lagrange interpolation technique. So for the Lagrange interpolation technique, we use two equations. The first equation, which is something denoted something like this, which is summation over I equal to 0 to n. I denotes the number of variables. Let's say I have 4 variables, then I is equal to 0 to 3. So if I have 5 variables, then I is equal to 0 to 4. So this is the summation over all the data points. So in all of the data points, we just multiply the function value f of xi divided by the Lagrange polynomial of that order. That means these L terms, Li of x, these denote the Lagrange polynomial terms. So what is these Li terms? These Li terms can be easily denoted something like this. Lix is actually the algebraic multiplication of these terms. That means we just determine all of these terms, where in the numerator we have x minus xj, and in the denominator we have xi minus xj, and we go through all the variables from j equal to 0 to n. So and we have to be careful about this term. It is j not equals to I. Here we are just given 1, it should be j not equal to I. That means whenever we are calculating for I equal to 0 terms here, in the Lagrange polynomial case, j is not equal to 0. Similarly, if we are going to find out I equal to 1 term in the first equation, then in the second equation j is not equal to 1. Similarly, if I equal to 2, j is not equal to 2. If I equal to 3, j is not equal to 3. So this is how the equation works. So we have to be careful about these j terms. J is not equal to I. So let's say I want to find out the equation, the Lagrange interpolating polynomial equation for the term where n equal to 1. So that means here n equal to 1 and I is going to vary from I equal to 0 to 1. So that means there are two terms in here, fn of x, there are two terms here. For the first term is for I equal to 0, that means L0 of x and f of x0, and the second term is going to be for I equal to 1, that means L1 of x and f of x1. So if you just calculate the equation, it would something look like this. So look at this. In the first case, I equal to 0, that means j is not equal to 0. That means these terms, the x equal to xj terms, that means x0 terms will not appear here. So look at this, there is no x0 terms in the xj terms, that means x1 here. Okay, so j is not equal to I, because if j is equal to I, the denominator, the here xi minus xj, this term would be 0. As a result, this whole interpolating term will become infinite. As a result, that's why this xj term is never equal to xi terms. So if you just calculate the Lagrange interpolating polynomial, it would look like this. This is for the linear version, that means n equal to 1. For n equal to 1, we would have to use just two data points, x0 and x1. So this is similar to the case of Newton's interpolating polynomial. We have seen there that for an nth order polynomial, you need to have n plus 1 data points. Similarly, for the first order Lagrange polynomial, you need to have at least 2 data points, that means x0 and x1. So similarly, if you want to extend the Lagrange interpolating polynomial for the second order case, that means n equal to 2, the equation would look like this. Okay, so this is just an extension of the first order case. So this term here, this is the L0 of x, and this is the L1 of x, and this one is L2 of x. Okay, so these are the Lagrange interpolating polynomial terms. Similarly, you can easily determine the equation that can be used for n equal to 3, n equal to 4, n equal to 5, and so on, whatever you like the order. So for second order Lagrange polynomial, there will be two terms in the denominator. Look at this, in the denominator there are two terms. In the first order case there were one term, but in now there will be two terms, and in the numerator we will also have two terms, and there will be three interpolating terms. So for nth order version, there will be n terms in the denominator as well as in the numerator of the Lagrange interpolating polynomial terms, and in total there will be n plus 1 terms in the whole equation of the Lagrange polynomial case. So this is the generalization. So please remember this, that for nth order polynomial we will have n plus 1 total polynomial terms. So Lagrange interpolating polynomial, it can be easily determined from Newton's formulation. Okay, so if you remember the Newton's formulation from the previous lesson, so you can easily see that this Lagrange polynomial is nothing but the extension of those Newton interpolating polynomials. So let's say, for example, we want to prove the first order Lagrange interpolating polynomial from the Newton's interpolation. So for first order, n is going to be equal to 1, and if you remember the first divided difference formula, it looks something like this. So this is the first divided difference formula, or we are just denoted this as the two variable functions, or it is just the first divided difference formula. Okay, this is just the first divided difference formula. So if you see that in the numerator we have f of x1 minus f of x0, and similarly in the denominator we have x1 minus x0. Okay, so if you just separate the numerical terms, that the numerator terms f of x1 and f of x1, just separate those two terms, we will get an equation something like this, which is f of x1 divided by x1 minus x0 plus f of x0 divided by x0 minus x1. So we have just separated the two terms in the numerator. So from lesson 28, that means in the last lesson, if you remember the Newton's first order interpolation formula, it looked something like this. So this is the Newton's interpolation formula, and this is the formula that we have just found using the first divided difference formula. Okay, so look at this, the f of x1 comma x0, the first divided difference formula, these actually appears in the Newton's first order interpolation formula. So Newton's divided difference, or the Newton's interpolating formula, was not just a new method, rather it incorporated the divided difference formulas that we just learned in lesson 4. So they are just the extension of those lesson 4 formulas. So this divided difference formula, the first order divided difference formula, actually appears in the Newton's interpolation formula. Okay, so once we have determined this equation 2 and equation 3, we just substitute equation 2, the first divided difference formula, into equation 3, and we will get an equation something like this. Okay, f1 of x equal to f of x0 plus this plus this. So these are the three terms that we get. So if you just group the similar terms, look at this, here we have f of x0, also we have f of x0, so we just take the common of f of x0 and just simplify the equation, and we will get something like this. So this is the Lagrange interpolation formula of first order. So what we have seen, we just substituted the first order divided difference formula into the main Newton's interpolation formula, and then we have just derived the Lagrange interpolation formula here. So that's how we derive the Lagrange interpolating polynomial from the Newton's interpolating polynomial. So let's look at an example. We are just given three data points, x0, x1 and x2, and the corresponding function values. So this example looks similar to the case that we have just seen in the Newton's interpolating polynomial example. So the same example we are just covering here using the Lagrange interpolating polynomial. Since we are given three data points, we can at most fit a second order interpolating polynomial, that means a Lagrange interpolating polynomial. So we can at most use the second order case. So you can also use the first order case, but the largest order of the polynomial should be 2. Okay, so we are just going to see both cases. In the first case, say for example the first order Lagrange polynomial, we need to use this Lagrange interpolating polynomial, and we have to find out the value of the function at x equal to 2. Look at this, x equal to 2 is not given here in the question, so we are just going to derive a interpolating polynomial, and then we just going to substitute this x equal to 2 term into that polynomial equation and get the value of the function at this point. Okay, so first we are going to find out the polynomial, the first order Lagrange polynomial, which is we have already seen the formula, which looks something like this. So in this formula we are going to insert all the variables here into this equation and get the value of the first order Lagrange polynomial. So if you see the value of the point x is equal to 2, so you are going to just substitute this value into x into the first order polynomial equation and get the value something like this, 0.4620981. So this is the value of the function at x equal to 2 using first order Lagrange interpolating polynomial. We can use the second order Lagrange interpolating polynomial. It would give us a more accurate result, and if we use the second order equation, it would something look like this. This is the second order Lagrange interpolating polynomial, and we are going to substitute all the variables here from the question, and x should be equal to 2 because we are going to find out the value of the function at this point, and it turns out to be 0.565844. So this is the updated this is the result when you use the second order Lagrange interpolating polynomial. So you see the result gives us a better accurate result than the first order case. Okay, so you can easily determine the result using the Newton interpolation formula, which were covered in the last lesson. So but now we have just used the Lagrange interpolating formula. So that's the end of this lesson. In this lesson we have learned about the Lagrange interpolating polynomial. We have seen how you can derive this interpolating polynomial from the Newton's interpolation formula, and we have solved an example with the Lagrange interpolating polynomial. So please try out the MATLAB code that I have attached with this video for Lagrange interpolating polynomial, and try to go through all the details of the course so that you can understand how this method is implemented in MATLAB. So in the next lesson we are going to try out another interpolation technique, which is spline interpolation. Okay, so that is actually the interpolation that is applied on a chunk of data of the whole database. So we will just look at the details of this spline interpolation in the next lesson. So till then, thank you so much.